Hello everyone, we are moving to section 4.4, linear independence. So we already know that we can build from sets of vector spans, right? Now, let's talk about vectors themselves in that set and set up a new definition. Vectors in set S, which has more than two vectors, two or more vectors, are called linearly independent if no vector from the set can be expressed as a linear combination of others. For example, you cannot express vector 1 through a linear combination of remaining vectors. Then they are going to be called linearly independent. But I'm not talking just about vector 1. None of vectors in a set can be expressed as a linear combination. Then we are going to call them linearly independent. If you can express one of the vectors through linear combination of others, set is going to be called linearly dependent. So kind of that's a definition of linear dependence and independence. I'm going to finish my definition with second part. If some vi can be expressed as a linear combination of others, the set is linearly dependent. Okay, well, that's kind of good. Now we're talking about sets of two vectors or more. Now, what is going to happen with set of one vector? For one vector, for a set of one vector, we're going to consider its independent if vector is not equal to 0 and dependent if vector is equal to 0. So if a set consists out of only one zero vector, like 0, 0 set, then we are going to call it dependent. If it has non-zero vector, even 1, it's going to be considered independent. Just you cannot express one vector as a linear combination of others just because that's only one vector, right? Let's consider a couple of examples. Example number 1. Consider a set of our standard vectors 1, 0, and the next vector is 0, 1. Is this set dependent or independent? Well, there are two vectors, right? So basically, can we express vector 1 as a linear combination of other vector? Well, we know that we cannot. No matter by what number we multiply vector j, we are not going to get 1 over here just because there is a 0 sitting here. Same is going to happen with j vector. We cannot express it as a linear combination of I vector. Just no matter what number you plug in here, if you multiply it by this 0, you are still going to get 0. You're not going to get this 1. So, linearly independent. Okay, maybe I should consider a linearly dependent set before I prove the theorem. Let's do example 2. Let's consider, I just pressed on something wrong. Let's consider as two vectors, vector A, which is 1, 2, and vector B, which is -2, -4. Let's write down that vector B can be expressed as a linear combination of vector A. If we multiply vector A by -2, we are going to get, this is vector A, -2, -4. So not linearly independent. I'm going to write down linearly dependent. Okay, very good. So we know that linearly independent, linearly dependent. Now guys, there is a good theorem which is sometimes used as definition too. Theorem. A non-empty set S, which consists out of some vectors. Non-empty means that at least one vector in it. In vector space V is linearly independent if and only if there is only trivial solution to linear combination of these vectors. So if we create a linear combination of these vectors, all of them, and set it up to 0, if we have only trivial solution means that on all k1 equals k2 equals kr equals 0, trivial solution. So if you create a linear combination and make it equal to 0, the only way to do this is to have all coefficients equals to 0. And this theorem also sometimes works as definition. Sometimes linear dependence is defined actually as trivial solution for linear combination. But again, can be either way. I'm going to prove it. So, not very complicated proof. So, we have non-empty set linearly independent, and I'm going to prove this direction. Linearly independent S is going to be followed by trivial solution of linear combination. That's kind of what I'm proving, right? Well, let's imagine that vectors are linearly independent, but contradiction. We have non-trivial solution. Assume we have non-trivial solution. Sum ki is not equal to 0. Well, I don't know, like let's assume that this is k1. Assume that it is k1. Again, can be any k, but for k1 it's going to be just easier to write it down. So what we can do, linear combination k1 v1 plus kr, wrong bar, kr vr is equal to 0 and k1 is not equal to 0. What we can do, guys? What we can do? I'm going to well, because k1 is not equal to 0, I can divide by it. Or let's say I can multiply left and right side of my statement by 1 over k1. And I'm going to have v1 plus k2 over k1 v2 and kr over k1 vr. Again, if it's not k1, if it's some other coefficient, you just kind of divide by it. Now, what I'm going to do, I'm going to move all this to the right side and just keep v1 on the left side. So v1 equals minus k2 k1 v2 and minus, actually I put plus here, but they're all going to be minuses. kr k1 vr. What we see, guys, these numbers, though they are looking complicated, that's just a real number over real number with minus. I'm going to call it k1 tilde, and this one is going to be kr minus 1 tilde. They're just numbers. So actually what we did, we expressed v as a linear combination. So v1 is a linear combination of others. What does it mean? Means that it contradicts to our condition given, linear independence, because if we can express one vector through others, they're not linearly independent. So we got our contradiction. Okay, good. We are going to move backward. Backward means that, let's say, a trivial combination, there is only trivial solution to linear combination and they are linearly independent. So I'm going to write it down. Only trivial solution. Then, well, that's going to be like opposite direction. So I put trivial solution first, then linearly independent. Well, let's imagine that we do have this, but it's linearly dependent. Linearly dependent means that we can express one vector through others. For example, v1 can be expressed as k2, v2, and k, I don't know, r minus 1, or kr actually, sorry. Kr, I'm always writing down the vector above k, kr, vr. So, like linearly dependent. Of course, it's probably not necessarily vector v1 we can express. Just let's assume that it's v1. I'm going to assume. Well, I'm going to move everything to one side. I'm going to write down v1 minus k2 v2 and all the minuses kr vr equals to 0, right? If I move everything to the left side. So I know that v1 at least multiplied by 1 here because it's expression for v1. So, and what I have actually non-trivial solution for linear combination. Non-trivial solution. k1 equals 1, not equal to 0. So we got again contradiction because it's only a trivial solution. That's it. Yeah, sometimes these two statements are so close to each other and we see that they are kind of interchangeable because of this sign, right? They are identical by consequences. So sometimes we are going to even use the theorem as definition of linear independence in some cases. Okay, well, let's consider kind of more examples of linear dependence or linear independence. I'm going to consider slightly different space of polynomials. We did not consider it yet in examples, so that's going to be example number 3. Let's consider space of all polynomials. All polynomials of degree less or equal than n. For example, you choose 2. So all polynomials of degree like 0, 1, and 2. And they're going to usually look like this. Going to look like a0 plus a1x plus anx to the power of n. So polynomials of this shape. Not necessary that they're going to have all the terms, all the coefficients not equal to 0, but just like maximum degree is possible like n. Now guys, let's consider a set of like next polynomials 1, x, x squared, and x to the power of n. Is it linearly independent? I'm going to show that it's linearly independent. We'll prove linear independence. Well, I'm going to use my theorem. So I'm going to set up a linear combination. I'm going to multiply the first constant by first polynomial plus a second by second polynomial plus a third by third polynomial. And, well, I'm going to have how many of here? here we are going to have n plus 1 terms. So I'm going to have k n plus 1 by x to the power of n. So that's my linear combination. And 1, x, and x squared, and all, they are my vectors. And I'm writing down vector 0 here, but this is actually just normal 0, just because for polynomials, vector 0 and normal 0 is the same. So I'm just going to switch it to normal 0. So basically, to prove that it's linearly independent, I'll need to show that there is only trivial solution to this. So the only way to satisfy this is to make all the coefficients equal to 0. Well, imagine that we have non-trivial solution. If we have some ki not equal to 0, then it's going to be a polynomial. That we are going to have a polynomial of n degree equals to 0. We do know that maximum amount of solutions here, n, the roots, that there are just n x's which are turning this polynomial into like 0. Let me draw the picture. Well, I don't know what is n, but let's imagine that we have something like this. So this is 0, this is 0, this is 0, this is 0, and this is 0. For this specific picture, there are 5 solutions. But depending on n, it's going to be like, so maximum solutions, or like x's which are turning it into 0, is n solutions. Well, there are n solutions, but what is going to happen to the rest? Like, for example, for this x, or for this x, or for this x, they're not going to be equal to 0. So we see that the whole polynomial cannot be equal to 0 if there are some non-zero coefficients. If you have some non-zero coefficients, it's going to have n solution at last, but not equal to 0 for all x. You see? Because this 0 means that it's kind of like constant. Let's function y equals 0, which is equal to 0 for all x. And for all x, we can turn it into 0 only if we set up all coefficients to 0. If one of them or two of them are non-zero, then it's going to have some solutions, but it's going to be like only 2 or 3 x's, or like n x's at maximum, which are going to be like equal to 0. The rest are not going to be equal to 0. So guys, we can consider as a linearly independent set. Okay? Well, kind of nice, right? To know that this set is linearly independent. We are going to use it in the future. Okay, let's consider next theorem, which is very kind of simple. Finite set that contains 0 vector is always linearly dependent. Well, how we are going to prove it? I'm going to build a linear combination looking like this. 0 by v1 plus 0 by v2 plus, I don't know, 0 by vk plus 1 by 0, and make it equal to 0. So my set S consists out of v1, vk, and 0. The set contains 0. So let's look at this linear combination. Is it equal to 0? Well, you multiply every vector by 0, it's going to turn into 0. Here, you multiply 0 by any number, it's going to turn into 0 too, so we have 0. But the coefficient of 0, the coefficient is equal to 1, not equal to 0. So non-trivial solution means linearly dependent set. You see? Okay. Another theorem. A little bit longer and more like complicated to write, but easier to understand. Next theorem. Let S, set S, consist out of some vectors, or vectors. Be a set in Rn, n-dimensional vectors. So these vectors are n-dimensional vectors. They are not strange vectors. They are just like our standard vectors. Theorem tells that if R, number of vectors in this set, is greater than n, then S, the set, is linearly dependent. What does it mean? For example, you are in two-dimensional space. If you have three vectors, they are going to be linearly dependent. If you have four vectors, they are linearly dependent. Two vectors, which is equal to dimension of the space, can be linearly dependent, cannot be linearly dependent, but three are going to be linearly dependent, no question. The proof is not going to be very complicated, but let's watch how I prove it. So that's going to be the proof. I'm going to express every vector in components form. My vector v1 has components v11, v12, v1n. Why it has n components? Because it's Rn. How many vectors I'm going to have? R. So my last vector is Vr, which is going to be Vr1, Vr2, and Vrn. Again, these V's are numbers which are like kind of coordinates of a vector in n-dimensional space. Now, guys, I'm going to build linear combination. So linear combination is like k1 by v1 plus k2 by v2, and the last one is kr by vr, and I'm going to set it up to 0. Ideally, guys, if you have only trivial solution to this, they are linearly independent. And to show that they are dependent, we'll need to show that there is non-trivial solution. At least one of case is not equal to 0. Okay, how are we going to do it? Well, I'm going to write down each of these vectors in like column form. So I'm going to write down k1 and the column v11, v12, v1 n plus k2 and same plus. The last one is going to be kr, and that's Vr1, Vrn. It's going to be equal to the vector 0, 0, 0, 0, 0. Well, if you look at this is what? Linear system of equations. What are unknowns in this system? These are unknowns. K1, K2. So how many unknowns? K1, Kr, are unknowns. How many equations we have? N equations. If you write it down, n equations. So we have number of equations less than number of unknowns. Just because the theorem tells that that number of n is less than r. So let's say we have two equations and three variables. What are we going to have necessary? Number of equations is less than number of unknowns. So what means that we are going to have infinitely many solutions, right? When we have number of equations less than number of variables, we are always going to have a solution. Guys, sorry. when something happened to my iPad, I turned the recording off, and now I don't remember when it happens. So I kind of continued lecture without doing recording. But let's see. I think I did explain this theorem, right? The theorem that when you have more vectors than number of coordinates in them, that the system is going to be linearly dependent. which is like proof is sitting over here. I don't want to prove everything again. So imagine that you have r vectors with r greater than number of coordinates in one vector. So you have, for example, 3 coordinates, but you have 10 vectors. Then these vectors are going to be dependent. And the proof is kind of very simple. So we write down each vector through coordinates, set up the linear combination. And if you write down this linear combination in the column form for vectors, you're going to see that we have like r variables and just n equations, and r is greater than n just by the condition of the theorem. You have more vectors than variables. Then you are always going to have a free variable because it's going to be like 3 equations and, for example, 5 variables. You're always going to have a free variable, which is going to give you non-trivial solutions. So the set is going to be linearly dependent. Now, I don't remember. I think for differential equations class, I just wanted to introduce Wronskian. Imagine that you have n functions, and they're not polynomials. They can be like any functions. The only condition is that they're supposed to be n minus 1 differentiable on like the whole number line. Like, for example, exponential functions, sine, cosine, lots of functions are n minus 1 times differentiable. And if you want to set up like or find out whether they're dependent or independent linearly, you can make up a determinant of the next shape. You place functions first in the first row. Second row you make out of derivatives of these functions and continue for the second derivative, third derivative until you reach derivative n minus 1. And you make a determinant and calculate it. If this determinant, which is called Wronskian, is not equal to 0 everywhere on number line from negative infinity to positive infinity, then your functions are linearly independent. And eventually, guys, we are going to prove it in differential equations. But here, I think we just can use it for like solving problems if we are dealing with non-polynomial functions. For polynomial functions also, this Wronskian is going to work. But maybe it's going to be easier just to solve system of equations for polynomials. But I don't know. You can also, polynomials are also functions, and they are not like, not all of them are n minus 1 differentiable just because like some polynomials disappear faster than n minus 1 times. But you can always differentiate the 0 more times and still get 0. Okay, that's end of the class. Hopefully I did not turn this off too early. I'm sorry, sometimes I press something and it stops either recording or stops showing me whiteboard.